So, in the last lecture what we did was we derived the Bloch's theorem, which is to say that psi of x plus n times a is equal to e to the power I k n a times psi of x, where k is labels the state and N A is any lattice translation by which is the lattice constant is A. Now, having done this, I also showed that we can have allowed values of k given by k times n times a is equal to 2 pi r, where r is an integer. It can be 0 or it can be plus minus 1 plus minus 2 etc. So, this gave me the allowed values of k, which were written as 0 plus minus 2 pi by n a plus minus 4 pi by n a etc. 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 Now, corresponding to this, we could identify the blocks, the tight binding states or the molecular orbitals that we had obtained by associating a k with the tight binding states. For example, k equal to 0 actually corresponded to a state like this, which was totally bonding, and state which is k is equal to pi by a corresponded to totally anti-bonding states, plus minus plus minus plus minus etc. And what does it actually mean? It means the following, that is, let me go to the actually what we mean by that. So, usually this e to the power I k dot r is a wave or is a wave. So, in other words, in one dimension I can write it as e to the power I k x. So, this will be in 3 dimensions, but I am writing it in 1 dimension. So, this is actually a wave, and if I just take the real part of the wave, for example, then it will look like this. So, when x is equal to 0, it will be 1 and it will go like this periodically on both sides. And what we have is, on this we have a lattice. The lattice is at atoms are at positions 0, let us say 1, 2, 3, 4, 5, 6 etc. etc. So, what you can do is, at these positions 1, 2, 3 etc., what we can actually do is draw a find the value of, we can find the value of the function e to the I k x, which will be like this. Etc. etc. Okay. So, if you take these values, e to the power I k x will give the tight binding wave tight binding coefficient of the atomic orbital at the position x is equal to n a, okay, at the position x is equal to n a. So, in other words, this is some kind of a continuous function that I have plotted for discrete values of the coefficients at positions x is equal to 0, x is equal to a, x is equal to 2a and so on and so forth. So, once I have all these discrete values, through these discrete values I have passed a periodic function, and the periodic function has a wavelength lambda. So, the periodic function has wavelength lambda, and we can associate a wave vector k equal to 2 pi by lambda. So, what we are going to do is the following, that is, let me look at how this satisfies the tight binding wave function, satisfies the tight binding wave function satisfies the Bloch's theorem. Let me prove it. So, what we have is psi of x is actually given by sigma over n equal to minus infinity to plus infinity e to the power I k n a phi of x minus n a. Now, let me actually translate the wave function by m lattice constants, so that I get psi of x plus m a, and this is equal to sigma over n equal to minus infinity to plus infinity e to the I k n a times phi of x minus n minus m times a. So, you see that on both sides I have translated it by m a. So, this I can actually write it in the following fashion. I can write it as sigma over e to the I k m a, I can take as a common factor, sigma over L equal to minus infinity, or let me still continue with n, and then at the next step I will introduce L, n equal to minus infinity to plus infinity e to the power I k n minus m times a phi of x minus n minus m times a, or I can say replace n in the summation by L equal to n minus m, and it does not make a difference because n is going over all integers from minus infinity to plus infinity. L can also go over minus infinity to plus infinity. So, that I can just write this in the following fashion, e to the I k m a sigma over L equal to minus infinity to plus infinity e to the I k L a phi of x minus L a. So, what you see here is that I have only changed, what I have done is I have only changed the index of the summation. The index of the summation is always a dummy index, it does not matter whether you call it L, M, N or anything. So, this will be equal to e to the power I k m a times sigma over n equal to minus infinity to plus infinity e to the I k n a phi x minus n a, because when you sum over all values it does not matter whether you call it L or N. So, this is equal to e to the power I k m a times psi of x. So, you will see that the tight binding wave function actually satisfies the Bloch's theorem, and that is a requirement that for that to be an eigenstate of the crystal Hamiltonian. Now, having said that, now let us see what I said that this is a wave function that I have. Now, let me see what happens when I change k to k plus some 2 pi L by I will change 2 pi L by a. L is an integer, okay. So, if I have a wave function which is given by sigma over n e to the power I k n a times phi x minus Na. This is my psi of x, okay, psi k of x. Now I want to see what is psi k plus 2 pi L by A of x. So this will be equal to sigma over n e to the power I k plus 2 pi L divided by A I have changed times Na times phi of x minus Na, right. So what this will be equal to? This is equal to sigma over n e to the power I k Na times e to the power I 2 pi L n times phi of x minus Na. Now we know that L is an integer, n is an integer, therefore Ln is an integer. So I have e to the power I 2 pi into integer is what I am multiplying my wave function by, and so that is equal to 1. So what we have is psi k plus 2 pi L by A of x is actually exactly psi k of x. So which means that k is not unique. K, the wave vector, is not unique, and there are several infinite number of k values, all have the same block function or tight binding wave function. Well, the question is, how is this possible? How can you actually have an infinite number? But that is trivial actually. If you think about it, it is trivial, and let me see why it is trivial. I will show you. Let me look at, for example, the k is equal to pi by A tight binding state of the 1s orbitals. So when I take k is equal to pi by A tight binding states of the 1s orbitals, I have plus is a antibonding molecular orbital. So I have plus minus plus minus plus minus etc etc etc. Okay. So if I plot the coefficient of the atomic orbital in the tight binding function, then what I have is, at this position I have plus 1, here at the next position I have minus 1, at this position I have plus 1, at the next position I have minus 1, and at this position I have plus 1, at this position I have minus 1, and so on and so forth. Okay. So now what we did was, we drew one particular wave which was actually going through all these points, and then we read that out as the wave vector k. Now you can actually have infinite number of waves which actually go through these points but have a different wavelength. For example, between here and here, so I am showing you the points between here and here, I can actually have another piece of the wave which is coming in, so that it will look like this. Okay. So if I have a value like this, then instead of going down straight like that, I could have actually gone up, down, and then come back. So this has a different wavelength, this is lambda 1, whereas this particular thing that I am looking at, this one has a value lambda 2, which is equal to 1/2 of the lattice constants, it is equal to 1/4 of the lattice constant, because I am only having one peak and one trough. So, what I am trying to say in general is that this wave that I am talking about is not unique. You can have several waves which are actually going through the entire points, all the points which correspond to the weight of the wave function at that particular position, and the number that you can have is infinite. For example, you know, in the case that I am looking at, when I am looking at plus and minus, so here you see that the wave function, the wavelength here is lambda is equal to this is a, this is 2a, lambda is equal to 2a, right, or I have k is equal to 2 pi by lambda, and that is equal to 2 pi by 2a equal to pi by a, right, that is the wavelength that I am looking at. Now, I could add to k equal to pi by a plus, say, let us say 2 pi by a, because 2 pi by a is just a reciprocal lattice vector, or in other words, I had shown earlier that if you add any integer multiple of 2 pi by a to k, then the wave function does not change in its form. So, I have put this k is equal to pi by a plus 2 pi by a. So, this is equal to what? This is equal to 3 pi by a. Now, the wavelength for this one lambda is equal to, let me call this k prime. So, lambda prime is equal to 2 pi by k prime, and that is equal to 2 pi by 3 pi by a is equal to 2/3 of a. So, I can have a shorter wave as I have described here, which is 2/3 of a wave which is going through that. So, in effect what happens is you can have an infinite number of waves actually going through that, and that is not going to change the wave function one bit. So, if it does not change the wave function, it does not change the energy of the states, and it does not change the physics. So, that is the reason why k can only take values in the range k less than k less than or equal to k plus 2 pi by a. Okay. So, why is it that I have a open interval on the left side here and I have a closed interval on the right side? That is because if I were to allow this also to take the value k small k equal to capital K, then you will see that there is a relationship between the two k values, which is bridged by a reciprocal lattice translation vector, which is 2 pi by a, and you will not be having the uniqueness of the state. Okay. Because of that, if you want to have only a single state, then you should have an open interval on one side and the closed interval on the other side. Generally what is done is we usually take k equal to minus pi by a, so that my values that k can take are usually minus pi by a less than k less than or equal to pi by a. Okay. And so, the energy levels that I am looking at will all be having k values for the 1s orbital or for the hydrogen atom, the chain of hydrogen atoms. The k values it will take are always between minus pi by a and pi by a, and the energy values are all given for these different values of k. Now, let me see how many states are present in this range. Okay. So, what we have to find out is how many states do we have between minus pi by a and pi by a. That is, how many allowed values of k are there. Another way of putting it is how many allowed values are there. How many allowed k values are there in this range. To do this, let us consider a system, a ring of n atoms. Okay. When you have a ring of n atoms, then k can take values 0 plus minus 2 pi by n a plus minus 4 pi by n a, etc. And let us assume that n is n atoms, and let us assume that n is even. Okay. Then it can go up to plus 2 pi n by 2 times a. Let me give you one previous value as well. So, if I give you the previous value also, it will mean plus minus 2 pi into n minus 2 by 2a, and then I have plus 2 pi n by 2a, 2na, sorry. Okay. So, this will be the allowed values. The reason why you will not have the minus 2 pi n by 2 a n or minus pi by a is, like I already said, they are related by a reciprocal lattice vector, which is 2 pi by a. Now, let us count the number of states. So, here I have one state, here I have two states, which is plus minus 2 pi by n a, and again I have two states plus etc., plus two states plus one state, and this is the total number of this one is n minus 2 by 2, because you are starting from 2 pi into 1 to 2 pi into n minus 2 by 2. So, which is you have n minus 2 terms. So, this is equal to 1 plus n minus 2 plus 1 is equal to n states. So, the allowed values of k in my case, when I put the periodic boundary condition and restrict k as is required by the single valuedness of the wave function, the number of allowed values of k between minus pi by a less than k less than or equal to pi by a is actually n states when n is even. When n is odd also, there is no, it is not different, we can do it very simply. When n is odd, we can do it the following way. If n is odd, then we have 1, we have 0 plus minus 2 pi by n a plus minus 4 pi by n a, etc., plus minus 2 pi into n minus 1 by 2 times 1 upon n a. So, this is the states that are possible. N minus 1 is, because n is odd, n minus 1 is even, and if I go to n plus 1, which is the next integer, then it will go beyond pi by a. So, that is the reason why I will not go there. So, you will see that this will be 1, this will be 2 states, etc., and 2. So, this is 1 plus n minus 1 upon 2 into 2 is equal to n states. So, whether n is even or odd, it does not matter, but the number of states between minus pi by a and pi by a are actually n states. Now, let us see how the energies go, because the tight binding wave functions is an eigenstate of the crystal Hamiltonian. So, the crystal Hamiltonian that we have looked at for the hydrogen atom is the following, that is, we have always taken phi n h phi n plus minus 1 is equal to minus t, and otherwise for all other elements are 0. So, let us look at whether this is actually the eigenstate or not. Consider a ring of 6 sides. So, when you consider a ring of 6 sides, then the Hamiltonian matrix is given by 0 minus t, 0 0 0 minus t, right, 1 2 3 4 5 6, yeah, and then minus t, 0 minus t, 0 0 0, 0 minus t, 0 minus t, 0 0, 0 0 minus t, 0 minus t, 0, and then 0 0 0, 1 2 3 4 5, yeah, minus t, 0 minus t, and the last one will be minus t, 0 0 0 minus t 0. So, this is the Hamiltonian matrix, because I have taken capital N is equal to 6, and anyway anytime you have neighboring sites you have a non-zero Hamiltonian matrix element. And I also look at one of the eigenstates. So, one of the eigenstates, one of the states that pictorial I showed was the state which corresponded to plus minus plus minus plus minus, and it is actually a cyclic thing. So, I can actually write it on a ring, it makes it look much better. So, if I were to write it on a ring, then what I will have is the following: plus minus plus minus plus minus, and what it means is that the wave function has the values 1 minus 1 1 minus 1 1 minus 1. So, there are 6 of these. So, if this acts on this state, what you will get is the following: you will get, see, the first one is minus t and minus t, that is minus 2 t is the first one, and so on and so forth. So, I can write it as minus 2 t times 1 minus 1 1 minus 1 1 minus 1. So, you see that this state plus minus plus minus plus minus plus minus that I have written down is actually an eigenstate of this Hamiltonian. So, we can get the energy of any of these states in general just by getting the this expectation value of the Hamiltonian between the tight binding states. So, if I want to find out the energy of the state k, then what I have to do is I have to do psi k h psi k divided by psi k psi k, okay. And my psi k that I am looking at is sigma over n e to the I k n a phi 1 s x minus n a and if I assume that integral phi 1 s x minus n a star phi 1 s x minus m a dx over all space is equal to delta n m. That means that atomic orbitals that I have chosen on different centers are actually orthonormal, then the normalized psi k x will have 1 upon root n sigma over n e to the power I k n a phi 1 s x minus n a. So, with this, if I want to find out psi k x h psi k x, so this will be nothing but 1 by n sigma over L sigma over m phi L x minus La, I mean sorry, not phi L, phi x minus La H phi x minus Ma times e to the power I k m minus L times A. Okay. Now we have phi x minus La H phi x minus Ma is equal to HLM is equal to minus T for m equal to L plus minus 1 and is equal to 0 otherwise. So what this means is that 1 upon n into sigma over L times let me see, is the x minus L. So I will have 2 cos Ka into T, the 2 cos Ka coming because I have L is equal to, I can take out a common factor for m equal to L, and then the other term will be plus minus 1. That is what I have, is I will have something like e to the power Ma well, you can, I mean it's trivial, I mean I do not know why I am trying to do that, but that is trivial. You can actually put it in this particular thing, and then you will see that once you will get when m minus L is plus 1 and the other time when m minus L is minus 1. So m minus L plus 1 and m minus L minus 1, so that will give you e to the I k a plus e to the I minus I k a, that will give me 2 cos k a into T, and then I have a normalization constant. So this will give me and L goes over all the terms. So there are n terms. So this is n upon n times 2 T cos k a. So in other words, I have an energy band which gives me the energy varying with k in the following fashion: E of k is equal to 2T cosine k a, and T is negative. I have taken minus T, so I might as well write it as minus 2T. So when I write it as minus 2T cosine k a, then I have the following, that is, if I plot E of k versus k, and my k values will go from minus pi by a to plus pi by a, and I have a dispersion that goes like that. So this is what is called the energy band. Okay, what I will do is I will stop at this point. We will continue with this in the next class. Thank you.